Hey, what's up guys? Coming to you here from the University of Southern Mississippi's beautiful campus. So hopefully you guys enjoy this. Hopefully you guys can hear me a little bit better since I'm not on the bike today. What do I want to talk about today? Well, I want to talk about bioenergetics, energy systems. How do we produce that all necessary and important ATP, adenosine triphosphate? So I'll talk about that today. Hopefully you guys can better understand that. So here we go. What is ATP? Good question. You should be somewhat in the know of what ATP is if you do any type of endurance athletics or any athletics for that matter. ATP, it is the monetary system, right, of our body. So ATP, adenosine triphosphate. So when we talk about adenosine triphosphate, we're really talking about the high energy phosphate bonds that are there. Now, adenosine is really an adenine and a ribose backbone, okay? That is that adenosine part. We're not really worried about that. We're worried about the high energy phosphates that are attached to it. As soon as the muscle uses that ATP, it doesn't just discard it completely. What happens is an ATP is broken off, right? Or I shouldn't say that. An ATP triphosphate is cleaved and one of those high energy phosphate groups is released. So what you do is you end up with an adenosine diphosphate. So now you have adenosine diphosphates and these inorganic phosphates. So that's important to know. It's important to reference because of the fact that ATP is constantly being resynthesized within our system. It was a hard word for me to say. Resynthesized within the system. So we have to make clear that ATP is limited. That limited supply can be anywhere from about 80 to 100 grams under resting condition. Actually, if you're talking about numbers or seconds, for all-out exercise, we have enough stored ATP in our system to produce maybe about 2 or 3 seconds of maximal exercise. That's not a lot of exercise. So there has to be other ways of producing this energy source. And we do. We have plenty of places that we can produce this. And really, in all reality, it's not production, it's a resynthesizing of this ATP. So we can do it both aerobically and anaerobically. Anaerobically, obviously, without the presence of oxygen. Aerobically, in the presence of oxygen. Pretty simple, right? Now, there are various systems, if you will, within these two, right? We can talk about anaerobic production in the 2 ways, or we can talk about aerobic production and the 3 steps. I don't really say ways or pathways because they're really a series of steps. Just remember, anaerobically and aerobically. Anaerobically without the presence of oxygen and aerobically in the presence of oxygen, because they really do happen in 2 different locations. But normally, and I think this is hilarious, in exercise physiology texts, most often they give a picture like this, right? Yeah, that's not a muscle cell, okay? Now, it's important to know that because the muscle cell is different from all the other cells within the body, okay? Now, it's nice to look at that blob of a picture and say, yes, the cytosol or the cytoplasm, and the mitochondria or the mitochondria. It's nice to look at it because it's really simple and easy for us, right? But we can actually look at the muscle cell and understand that it is different. And we actually call that cytoplasm that we see in the blob something different in the muscle. We call it the sarcoplasm. Okay. Now the sarcoplasm is where anaerobic production of ATP takes place. There's 2 ways in which we can make ATP or resynthesize ATP within our system. 2 pathways. The first one is called the Atp Pcr system. Okay. Adenosine triphosphate phosphocreatine system. In this Atp Pcr system, what we actually have is we have these high energy phosphocreatines. As we use ATP within the muscle, once again, it breaks off, it splits into an ADP, adenosine diphosphate, and inorganic phosphates. Now, we have other phosphocreatines that are ready to bond to these ATPs, and this cycle is continually happening, right? There's about 4 to 5 times more phosphocreatine within the system than there is ATP. So ATP alone, body stores within the system, only lasts about 2 to 3 seconds. So your body can resynthesize that ATP that was spent or that was utilized by the muscle, and it can continue this exercise for maybe about 10, 12 seconds max in trained individuals. The second way in which we can resynthesize ATP anaerobically is what we call anaerobic glycolysis, right? Sometimes it's referred to as fast or rapid glycolysis. It is with the breakdown of carbohydrates or glucose molecules. So when we talk about anaerobic glycolysis, our end product is lactate, right? Our end product initially will be a pyruvate, and without the presence of oxygen or in the presence of low oxygen, what we do is our body forms lactic acid. Traditionally we used to think of this as being not beneficial for our system. It was harmful for our system. We know that's not the case. We can actually use lactate and it works to our benefit in the long run. That is true. But when we need energy right then and there, it kind of limits us, right? Now we can break down this glucose in anaerobic glycolysis and we can produce energy. We can produce actually 2 ATPs is what we produce off of it. We initially have to invest 2 ATPs, but with anaerobic glycolysis, we get 4 ATPs. So invested 2, got 4, take those 2 and 2 out, and our net production of ATP is 2. However, this only lasts for about, maybe push this up to a minute, maybe 90 seconds, somewhere in that range. It can be greater than that. It can, but in highly trained individuals. Now we're talking probably about some elite athletes here, but we're gonna have to start producing energy in a different form. And that's where we get into the big picture of aerobic glycolysis. So hopefully you guys remember a little bit from the video that I posted not long ago about muscle fiber types. If you remember, I talked in there about muscle fiber types and their different energy systems. Aerobic production takes place in both the sarcoplasm as well as inside the mitochondria. So if you remember something from that video, I talked a lot about type 2A fibers. Okay? Type 2A fibers are our friends as athletes. Doesn't matter what type of athlete you are. Why? Because type 2A can use both what we consider to be glycolytic and oxidative ways of producing energy. So there's really, or maybe 3 ways or 3 steps in which we produce ATP aerobically. What we have is we have that initial aerobic glycolysis. Sometimes we call this slow glycolysis. From there, once we actually have that glucose, it is broken down in the glycolytic cycle, our end product is pyruvate, okay? Pyruvate is important because in the presence of oxygen, pyruvate can be shuttled into the mitochondria. Now, the second step in aerobic glycolysis is what we call the Krebs cycle. I'm going to confuse you here. The Krebs cycle, the TCA cycle, and the citric acid cycle. They're all the same. It is the same cycle. There's just a lot of different names for it. And the third step along this pathway is what we call oxidative phosphorylation, or the electron transport chain. So aerobic glycolysis, the use of a glucose molecule, carbohydrates, right, breaks it down in aerobic glycolysis. Our end product at the end of that is a pyruvate. From there, that pyruvate can be shuttled into the mitochondria through the mitochondrial wall, and almost immediately gets broken down into something that we call acetyl-CoA. Now, this is the first part of respiration. As soon as that pyruvate goes and gets shuttled through the mitochondrial wall, what happens is we actually get what we consider high energy electron from that. We also get acetyl-CoA, and this is where we see the first oxidative respiratory process take place, and we create CO2, a byproduct of oxidation. Inside the mitochondria, one of the first byproducts that we get, CO2. Now, the Krebs cycle is kind of what we consider the keystone. It is the backbone, if you will, of aerobic production of ATP. Now, I say that because the Krebs cycle is the process of breaking these molecules down, these acetyl-CoAs down, into smaller and smaller forms that we can then move forward in the system and use for energy. Now, we can get to this acetyl-CoA a few different ways. It doesn't always have to be through glycolysis. But acetyl-CoA is like the barrier. It's the keystone, if you will. It holds up aerobic production of ATP. So we can get to acetyl-CoA through something that we call beta oxidation, and that's the burning of free fatty acids. Maybe I'll talk about that in a later video. And we can get there by deanimated proteins. So just remember this, acetyl-CoA is the keystone here. We can get to acetyl-CoA in a few different ways, but we primarily do so in exercise through aerobic glycolysis. You hear about this a lot. You hear the Krebs cycle, the TCA cycle, or the citric acid cycle, and how important it is. And yes, it is important. It's the keystone, it's the backbone. But it's kind of funny because ATP production is really not that high. There's very little ATP that is produced. Actually, for every pyruvate that comes through the mitochondrial wall, we actually only get one ATP. Now, at the end of the glycolytic cycle, we actually get 2 pyruvates that come out of 1 glucose molecule. However, the Krebs cycle produces so many other high energy electrons that they're very important, and they're going to move forward into the next step of oxidative phosphorylation. If ATP is the body's currency system, then the electron transport chain is the moneymaker. It is the federal bank. It is the way we produce ATP. Now, out of that single molecule of glucose that we talked about in these steps, right? Aerobic glycolysis, coming from glucose, a glucose breakdown, through aerobic glycolysis, in through that prep step, and now through the Krebs cycle, there's not a lot of ATP that was produced. But all those initial steps has actually created all of these high energy electrons. And in this electron transport chain, we're going to utilize those high energy electrons. Those high energy electrons are called NADH and FADH2. But just know that these high energy electrons will then go through what we call the electron transport chain in oxidative phosphorylation in order to produce a lot of ATP. As I mentioned to you guys before, oxidative phosphorylation, just like the Krebs cycle, takes place within the mitochondria. And actually it takes place in between what we consider the membrane of the mitochondria, the inner membrane, and the membrane of the mitochondrial wall. What happens is we actually get these electrons that are removed from this NADH and these FADH2s, and they move through these highly charged electrons, move through these things that are called the cytochromes. So through these cytochromes, we actually get the pumping of these hydrogen ions. That produces what we call an electrochemical gradient. So as these hydrogen molecules pass back through the membrane, or as they diffuse back through the membrane, we trap that high energy and we create or resynthesize ATP. Now that's through a process that we call Atp Synthase, but really what we're doing is we're trapping these high energy hydrogen ions, okay? We're trapping them within that bond of those phosphates, ADP and inorganic phosphates. We're trapping them in that bond. Now this happens by simply making this electrochemical gradient across the inner membrane and the membrane of the mitochondria, as you can kind of see in the picture right here. So just a quick overview here. What I want you guys to remember is that anaerobic production of ATP and aerobic production of ATP take place in 2 different locations within the muscle. Anaerobic glycolysis and Atp Pcr system, that takes place outside of the mitochondria. Aerobic production takes place just outside of the mitochondria and inside the mitochondria. Now, those 3 steps in aerobic ATP production are aerobic glycolysis, the Krebs cycle, and the electron transport chain, or oxidative phosphorylation. Now, as you can see in this picture right here, we can see kind of maybe the locations of where these are taking place. Now, you can't see on this picture where the Atp Pcr system is actually resynthesizing ATP and ADP. However, here, this is like a very elementary view of what we consider to be a mitochondria. And you can see glycolysis, the initial step of the pyruvate coming through that wall. You can see that initial step of creating some high energy electrons, CO2 production, as well as an ATP and acetyl-CoA, that keystone, if you will, of aerobic production of ATP. And then the Krebs cycle. And you can see that the Krebs cycle only produces 2 ATP. And it produces 2 ATP because of the 2 pyruvates that come through the wall through glycolysis, right? But you can also see that the Krebs cycle is producing a whole lot of these electrons, or these highly valuable electrons, high energy electrons that pass into the electron transport chain. And then you can kind of see here with the electron transport chain in the mitochondrial wall, actually producing this electrochemical gradient that produces ATP in the long run. So why is this important? Why do we talk about this? Why is it such a big portion of, for instance, my exercise physiology class or any exercise physiology class? Well, it's because we have to understand these systems and at what intensities they are taking place, and they help us train individuals. So we have to understand that at different intensities, we use different energy systems. Now, the electron transport chain is great, the Krebs cycle is great, aerobic production of ATP is amazing, but we have to understand that it takes place typically at about below that 75 to 70% mark in trained individuals. And when I'm talking about 75 to 75% mark, really what we're talking about is VO2 max, right? So at around 70 to 75% of VO2 max, we typically start to go into anaerobic type capacities. Now, one thing that we have to remember or distinguish is that these energy systems don't happen in a sequential fashion all of the time, right? So we can actually be producing energy anaerobically while still producing energy or ATP aerobically, and vice versa. In exercise, when we initially start, it's all going to be anaerobic. Most of the time they are continual. They're happening at different times. So we're talking about percentages. How much of a percentage we're actually utilizing aerobic versus how much of a percentage we're utilizing anaerobic production of ATP. And it's important because we have to understand that anytime we train, it doesn't matter if we're going to go out and do a 5K, or if we're going to go ride the bike for 2 hours, or if we're just going to go lift weights, okay? We have to understand that what we're training is an energy system. We're not necessarily just training that muscle per se. So when we think about this, when we go out and we lift weights, we think we're just getting the muscle stronger. That's true, that is true, but most of the time we're actually doing that by training an energy system for that muscle to then be stronger and then to grow because we're demanding more of that energy system. So this is an important distinction that we really do have to understand as athletes. I don't care what athlete you are. This is important to cyclists especially, and especially in something that we would consider a base season. A lot of the times we get bored in these base seasons or this base part of training because we say, man, I just have to be at zone 2 today. Can I just go out and do some sprints? Or can I, I'm just gonna attack a couple of times today. Well, I mean, you can do that and you can go out and you can train that way, but you have to remember that when we're doing this like zone 2 training, what we're doing is we're trying to train that aerobic system to efficiently produce ATP without variance. Now, later on, we can start mixing in training protocols that differ from this, right? Adding some sprints into the mix or adding some short burst VO2 into the mix, those types of things. But really what we're trying to do in base zone 2 training is we're really trying to produce this Krebs cycle ATP production, this oxidative phosphorylation ATP production. And in turn, what we also start to do is we start to become very efficient at utilizing free fatty acids in order to make acetyl-CoA, okay? So this is where we get into utilizing body stores of fat, for instance, as an energy source in this oxidative phosphorylation cycle. So it is important. If we understand these energy systems, we're going to become much more efficient at utilizing and training these systems, okay? When we are training, we are specifically training energy systems, okay? We have to remember that. We're training one of these systems, either aerobically or anaerobically, in order to do more work for us and produce more ATP. All right, guys, hope you enjoyed that video. It is something that is very close to me. I'm passionate about, obviously, and maybe I got a little confusing about it because I do get a little anxious. And I promise I'm working on that other video that I told you guys about a few weeks ago of heavy weight training and what that would look like for a cyclist. But if you guys do have any questions, go ahead and leave them in the comment section below. I typically respond to those pretty quickly. If you guys like the video, go ahead and give it a thumbs up. If you guys wanted to learn more about exercise physiology and maybe some cycling related stuff, you guys can go ahead and subscribe and hit the bell button if you'd like. Either way, thank you guys very much for watching, and I'll see you here next time, guys. See ya.